So hello everyone. I think we don't have enough time, but I try to finish what we should do for today. So the first point that I want to declare for you, starting from this simple program, just I want to paint something that you could understand. But I will use this one, and I'm not sure if I could deliver what I can do. So if we have a reservoir, and this is well, and let's say if we represent the pressure like this, sorry, yeah, so this is the pressure, yeah, and if we say this is under saturated reservoir, so all this reservoir will be above bubble point pressure. So here we for this fluid here inside the reservoir will be described by CCE. Oh, sorry, I have just this. So no. So if we are above bubble point, we have just CCE. So from CCE we know the PVT properties for the fluid. The second one is more difficult, but I will try to draw it. If we are talking about saturated reservoir, then this reservoir can be divided to two parts. Yeah. Sorry for this. So now if you are talking about a pressure, saturated reservoir, then the pressure, as we go near to the well, the pressure will be double. The pressure should be like this. And then at this point, we will have saturation pressure. It means at this case, we will need CCE to describe the fluid properties in this region and DLE in this region. You can note that in DLE and CCE we only do these experiments in reservoir temperature. We don't change the temperature because we want to simulate the oil properties inside the reservoir at reservoir temperature. In this, we have only pressure change. However, from the well here to the separator, this represents the separator experiment in PVT lab. Is that clear? Yeah, that's why we have CCE DLE in lab in PVT lab. So can you just open the Excel sheet where we have CCE data, and we will try to calculate Y function. So does everyone have this one? If someone needs a copy, we have. Then so the first step. Yeah. So the first step, it says define a constant composition expansion CCE experiment in the PVT software and enter the measured data from page 4 of the PVT report. We already have this here, I will show it to you. Yeah. So this is the data, and we already have them in CCE in the Excel sheet, and now now we will try to continue our work or our project in the last files. So I hope that everyone has already saved his project, and we will need it now. Yeah. So I think we have reached this point here. So maybe someone delete all those steps if you don't, if you are going to save this file as a new file for DLE. So we start from the last point on saturation pressure. I said DLE, I think it's CCE. Now we will do a project for CCE. So maybe we have saved this file as saturation project file. So we don't need all these files. So we can only keep this, delete all of those, and rename this file as CCE project. How can we delete? I think it's easy from here. Just select yeah. So now we have our new project CCE with the last data from saturation pressure. So the first step to define the CCE data inside this project. So we, as we usually do, we press this button to enter lab data. Then we need to go to CCE.
All of them except the 14.
Yeah, the last one. Because we will continue from last one. From this one. So now we will define CCE. We need temperature, pressure, and relative volume. This is what we have here. Since the temperature is constant in CCE, you don't need to repeat that. Just enter one value here and then enter the pressure. Yeah, from experiment, then we go to CCE. So now I will copy the pressure. And you have always to make sure, do we have the same unit or not? So now it's the same. Do you remember we said last time when we after matching saturation pressure by binary interactive coefficient, when we try to match density, we do this by autoregression because we need to keep more than 1 point matching. So you cannot do this manually. However, if you try to do it, maybe it will take long time. So when we use auto-regression, we have to give weights to say the software focus on matching this more than that. So usually we give the highest weight for the saturation pressure. And we say, maybe this answers your question. In PVT box, we give for PSAT 40, it's like a number, just 40, because they go from 40 to 1. So for density, they give 20, and for volume they give 10, and I don't remember what they give for other points. But this is the main weights that you have to give. So in the PVTP, they have from 10 to 1. So when 10 can refer to 40, so we can say something like this. They change it in the software, so this system you follow just in PVT. However, in PVTI, for example, in Eclipse preprocess software, you might use the same numbers. So this is for PVT text box.
Maximum.
Yeah. And they say this is the recommended values, and you can maybe give more than 40. But in the software, they give fixed range. You cannot give, for example, 11 here, but you can give 50 in the equations. So here, what that can mean for us, in this point here, we have to give, I entered this in the wrong column, so I have to fix it. Here. However, this is volume. Relative volume is just a ratio between the total volume and volume at saturation. The volume in each pressure stage divided by the volume at saturation pressure. So we will give weight for this value, and it should be 1. Or not 1, it can be 3 or 2. Let me just check. Because we say if we have from 40 to, you can consider this too low, 2 or 3. It's not big difference. How I give weight, I just select all of them and choose 2 and set weight. What? We said in text box, they said for volume you need weight 10. It's recommendation. But in the software, the range for weighting is changed from 10 to 1. This is your maximum weight and this is your lowest weight. So 10 can refer in this scale can refer to 2 or 3. So we use now 2. Yeah. When you do auto-regression, you give weights for properties. In calculation, this weights will when you try to match, it means that if you have the highest weight, the software or in the regression process, you will try to focus more on matching this. So, but in textbooks we have weights from 40 to 1, but in this software they changed that. They said the maximum weight is 10 and the lowest weight is 1. So those are the recommended weights for each property, and we choose the corresponding value inside the software. Maximum weight is 40, can be 10 inside the software, and we run PVTP and PVT textbooks. If you read PVT textbook, you will see that they recommend those weights, but you will not have the same scale inside the software. You can take just two. It's just how you refer to 10 inside the software. I can refer to that as 2. 20 is in the middle. Okay, so now we have entered the CCE. So what can we do now? We can simulate this experiment by this button. Here I enter the lab data. From here to here I use the equation of state to show the phase behavior, to calculate the saturation pressure, the PC and TC, and CCE, and so on, CVT. So each time you enter lab data, you will need to simulate that, and you compare the data which you have from your equation of state and the data from the lab. And then when you compare them, you will know how much your results or your equation of state is able to reproduce the same results. If we, I think the recommendation for the volume, it's already written here, so you will understand this. So in step B, it says run the CCE experiment and compare the simulated results with the measured results, reporting the absolute average error for the undersaturated oil compressibility, relative volume, and Y function. So now we will try to simulate the CCE experiment. As I already said, for equation of state, you will need, when you try to simulate any experiment, you will need to go through these. So we need to simulate CCE, which is this one here. So we have two ways to simulate the CCE. Either we define to the software which pressure points we need to calculate the relative volume for, or we just say to him, calculate the points that you already decide. He can do that. We will choose just points for you, and then he will do it. But don't use this, because we will compare each point. So we need to define which pressure to compare the same volume, to compare volume at the same pressure. So you need to do it like this. We enter, take the pressure, so now we enter the temperature, and as I said, we don't need to enter that at each row, so just one value and all the pressure stages. And if we say calc, you see that the software already reversed the values. Yeah. So now we can press calc. But just pay attention to this here. When the software calculated takes the pressure values, it reverses the way how it is organized. So it's not from when you take this data and you use it in Excel sheet, just pay attention to which one is in above and below. So okay, here there's a problem. The software just took the values until this row. It did not calculate all the pressure stages because he refers to those rows with the gray one. The gray one, it means that you need to enter the pressure in only those rows. But here, the software will not consider that. So what we can do, we take those values and put it in the next column. Or maybe someone will try with the software how can he make this with a gray color as this. I have not tried that. I can just do what I usually do. So I take. This is the way how the software works. It just so we need just 3 columns. No, we have 3 columns. So when we press calc, so it starts from the lowest pressure to the highest pressure. And if we want to compare this with lab data, which we have already entered, we can just press plot and we go to variables and we have to choose this one, relative volume. And then the software will take the relative volume data from the experiment data which you have entered and will show that data with your CCE data. So you will know how your equation of state is it able to predict the CCE experiment data or not. So when we draw both of them, we always represent the lab data with points and the calculated data with continuous lines. As you see that our equation of state is already able to produce the same values. However, we should calculate the absolute average error for those values to compare them. Because by drawing, you cannot know how much the average absolute error. But it looks, when you see this, it looks like you have a low average absolute error. And what we will do now from or in Excel sheet, we will try to calculate the average absolute error.
What factors could have currently affected this fish or not really able to match these points? What factors? If you are choosing 38.
Yeah, not now. Just we will reach that point.
Just asking, like, if you are choosing 30, will it have affected this matching?
Now there is no matching. We just the first step. We always compare results before trying to match. Last time you remember, we just saw the saturation pressure before we try to match. Then we check. So now we found that we already have match before trying to match, and that's usually happened in CCE experiment. In CCE, usually equation of state is able to predict that in low absolute average error. So now we will need to calculate the absolute average error for the oil compressibility relative volume and y function. Let's start by absolute average error for relative volume. So what we will do, just we take the relative volume, so yeah, this one relative volume, and we will go, it's oh. But you will need to, we copy now the values, but we need to rearrange them because in the software talks the values from the lowest threshold to the highest, and here we show the results from the highest to the lowest. So we have to reverse this. This is easy inside Excel. You can do that by oh. So now we arrange it just the values in this column. And we can say this is also relative volume, but this is from equation of state, and this is lab. So now we have relative volume from lab data and relative volume from equation of state. Now we will calculate the average absolute error, and
How do you flip it?
so we already have the here how we can calculate average absolute error, and I will try to do it now. So the first thing you need to calculate to degrees the calculated data from measured data and divide them from the measured data. And when you decrease, you need to put that you need to take that as absolute value to ignore the. So we say abs. So this is how we calculate those values. And to calculate the So what we have done here, we just take the summation of all. Here we calculate the average absolute error for between 2 points. So we have a small error, we add up all the errors. Then we take the average by dividing the summation by the number of points. So we have very low error. It's just less than 1%. And it's already said here in the last point that if it says that try to match your CCE data to minimize it to make it below 1%, but we already have it below 1%, so we don't need to match CCE data. And this is the way it is. Here it's simple. You try in other PVT data, usually you will have maybe 2% or 3%. Then you will have to go back to the software. I know at the beginning, for example, I compared this data with lab data, and I found I have error, for example, 2%. Then what I have to do, I close everything here, and I go to regression. Then I will have CCE data here. Then I can check it, and I use log. I've already said that I have two weight factor for volume, but I need also to check it again here as log. So if I said in a case that I saw that the average absolute error is more than 1%, then it's better to try to fix this value to improve your equation of state. Yeah, at each time you will need to take the lab data, put it in Excel sheet as we did here. So let's say if we compare, if we say simulate, and we we enter the CCE data here, and we take the values and put them here in Excel sheet and calculate the average absolute error. In case that you have average absolute error more than 1%, it's better to match this to CCE data. How you do it? You will need to go back to the software and go to the regression, give medium weight, and also include your CCE data in the auto regression.
If we don't do it, we use this kind of log data. Because for this density, you first didn't like tick a box, but you look through it and you
Yeah, this is what we do exactly.
You have to always do it. You have to always tick the box.
When you click, at the first time we just matched this without matching this, because we thought if we match this will not be sticky. But we found when we matched this one was sticky. So that's why we can't check both of them, because we want to match this, but we want also to keep this match. Now the process is a little bit more difficult. You need to match this, but you need also to keep those ones matched. So you cannot ignore them. You have to take those steps.
What about the weighting? You have to always follow.
We already entered the weighting when we enter lab data, and here we repeat that. So we do twice. And the more data you have here, the more difficult is to have matching. So in here we have saturation pressure, we have CCE. Next step we will have DLE data, and we will have at the end separator data. Then you will need to keep all of them matched at the same time with acceptable average absolute error. So fortunately we take this step by step. So we finish it. saturation pressure matching in a saturation pressure project, and now we are talking about CCE. So when we match CCE, we need to keep those matched. However, we found that the equation of state is already able to produce CCE data with acceptable average error. So we don't need to match relative volume. So now we have calculated the absolute average error. We have calculated the absolute average error for the equation of state, and we found that we don't need to match that. But before all of this, have we checked if or have we done the quality check for our data? We did not do that because the first step should always be that you check your data, then you use that. Then okay, my data is fine and I can now use it. So why we start like this? We start because we already know that this data is textbook example and there's no errors. But now we will apply y function and we will see how can we use this function to evaluate our data. Yeah. Equation 4? Yeah. This one. The software will not calculate average absolute error for you or will not do y function. Those things you need to do by yourself. That's why the software will not do everything. You have to understand. Yeah, you have to work in Excel and the software. So if we want to calculate the y function, we can calculate it from here. Just take the pressure at saturation point and divide it by the pressure for that point, and the same pressure is taken here. Then the relative volume. If you have that pressure, if you have the pressure in PSI gauge, when we decrease those one, it will be the same for either PSI gauge or PSI. But this one you will need to convert it. So if we use PV pressure with PSI, you take this value will be the same here. PSI here, and when we decrease, we will be PSI. But if the pressure is PSI gauge, then you can put the values here directly, or you convert them to PSI, you will get the same values because you take the difference. And here, this one you will need to convert it to the PSI. So this one should always be PSI. Those can be PSI or PSI gauge, but this one should always be PSI. Pay attention to this, it's important. So now we will try to apply the equation. We start calculate our y function below the saturation pressure, and to make this fixed, you need to press F4. You will see that our pressure here is PSI gauge, then we need to convert this to make it PSI. And you will see that we could calculate the same values for what the lab has reported. The lab will sometimes will report to you y function, and when you calculate, you will be able to see that you can produce the same values. So now we have to how can we evaluate our relative volume data here below the saturation pressure? We will need to draw that. So the points, they appear like on a straight line. So it means that, okay, your points are measured correctly. However, we usually use best fit straight line to draw a straight line and see. You usually found that there is points like this here. So maybe it's better to ignore the points, the first points from here, because they are already those points which are near to the saturation pressure. So we usually ignore when we do best fit, we do for those points. How we add best fit line in Excel? We just press right click in the chart and add fit line. And we say linear or linear. I did this for the all points. I take just all points if. Oh. It's okay to do the straight line for all points. Now, let's say that the lab data should follow this straight line. And what's the benefit from this? We can recalculate the relative volume which follow this straight line, which means that that volume is corrected. It's not existed here. You can find it in your PVT manual. However, the steps how you calculate this, they are mentioned in the last chapter. This one, this page. It's like divided to steps. Step 1, step 2. And this is the last step, step 4. when you calculate corrected relative volume by this equation. Okay, page 95, 113. It's
Could you give a page?
yeah, 95, 113. It's the way how this. It's in the appendix. Okay. So we do this just in case that you have you saw that there's error in your lab data. So you start by y function. Just remember the steps, they are mentioned in the appendix. So just you can have a look on that procedure. So we start by one y function to evaluate the volume properties below the saturation pressure. So, and from the chart, we know how data will look like. Are they in a straight line or not? If they are not in a straight line, you will need to fix the relative volume. So you will have lab relative volume and you will need fixed lab relative volume. How we fix that? By y function. How we calculate that? You have a small equation and you can try that in your Excel sheet.
I follow.
95 in the upper If you see to the question, you will see that you have A and B, and A it's one of them it's the intersect, and the other one is the slope for the straight line, and you can find that here from your chart. This is the slope, and this is the intersect. However, sometimes Excel sheet will show you few digits, and that may affect your results. So you might go to the properties and change this to show more digits. Yeah, here the number of digits that you want to see. So now I am able to take the value for my slope. So the slope will be B value, which is here, and the intersect is this one.
You don't need to calculate F4 again?
Oh, okay. So you see here we take more than 4 digits before number. Yeah? Yeah, exactly. You need to convert that. That's why I keep it to know who's paying attention.
Which one is A and B?
We have A here and B here. A is the intersect and B is the slope. Straight line equation. And now we can apply this for all. And you can see now, even after correction, the values are still nearly the same. But those one are the corrected value, and those one are not. If you correct the relative volume, I think in the software you will need to use this one, the corrected one. I'm not sure about this, but I asked Professor Gans and he said you can take this in case that it's corrected. There's a law, because what we already do, we match this data with this lab data, and we calculate average absolute error. So in this case, if we match this with this one, we don't need to put the corrected one. If you found there is mistake here in lab data, if you have lab data and you evaluate that data by Y function, and you saw not all points are on the straight line, it means that lab data you need to correct them. Then you correct lab data, and this point I'm not sure about, but I think you will need to enter those relative volume in the software. You need to match those points, not lab data points, because you can, if you match wrong points, you will maybe destroy your equation. So in this case, we already have low error. I repeat, just to make this clear. In this case, we have already low error, either when we do it by Y function or by equation of state. So it means our lab data is okay. But in case you have another lab data which you are not sure about, the first step you should do is start by Y function. From Y function, you recalculate relative volume. And in the software, if you found that there is big difference between the corrected volume and the lab volume, or lab relative volume, it's better to take the corrected one.
But here,
It's the same. Maybe in your 10 project. I will not decide this, but
what kind of difference? That means one is gonna be like 2, for example.
you can see that in the chart, or you can also recalculate average absolute error. Again, we will try to do it now to compare this with this and see the average absolute error as a number, as one number. So maybe we do it again. It's the same. We take this.
So we need to do that.
So you will see if we calculate the absolute average error, but this time between the corrected relative volume by Y function and the relative volume from lab measurement, you will see that you will have very low absolute average error. It means like your Y function says to you your volume is measured correctly. Is that clear?
Is that the way you can put that, you can bring that error to 0%?
Okay. If you want to make this 0, you will take your lab data the same which you use the corrected one. So I can take the corrected one and if you calculate the error between the same points, it will be 0.
I know, but I'm trying to
Inside the software, input it and try to match this and do the same steps here to visualize this again. I think the lecture is finished, but I still need some more minutes. If someone wants to go, he can go now, and we will upload the video for this lecture. But I hope that some students will stay to pay another 15 minutes maybe to complete this. If you don't have a problem, it's okay. So now we compare it, relative volume, and we know that our relative volume, no problem, I have a lot of things. So, we know that our relative volume is okay, we could match this from the equilibrium state, but now we need also to compare the compressibility we already compared, we already calculated the absolute average error for relative volume, and we already showed the Y function, and now we will calculate the oil compressibility. Professor Ganser said oil compressibility, how that is calculated, we will see it now. So, from lab data, compressibility always is calculated between 2 points, because we have a high pressure, we reduce that pressure and the volume change, and we will know from that how our oil can be compressible. The change with volume when we change pressure. So we have just 3 values from 5,000 to 4,000, 4,000 to 3,000, and so on. So here it says PSI, while all the report it says PSG. Can you know why?
PSG.
Why here it's PSI, not PSG?
Reservoir.
It's also here measured. We calculate that from relative volume, and we calculate that from measured from relative volume. It's PSI. It can be written as PSI or PSI gauge, because when we calculate compressibility, we take the difference. And no need for that. Okay, so the problem with compressibility, I don't remember actually how it looks like, but when it's mentioned in page, you can see that in William McCAIN page 231. It's the third reference here. How you calculate compressibility. So compressibility usually volume pressure, it usually looks like this. And this here, it's like straight line. So they take a straight line equation and they do it to calculate this from slope. But here, when we go near to the focal point pressure or saturation pressure, the slope changes like this. So that's why when we are near to the focal point pressure, we need another equation here. So here we have equation, and here we have equation. And that's clear here in your guidelines. It says to you as a hint here. Use this equation when your pressure is above focal point pressure. And use this equation when your pressure is near to the focal point pressure. So compare it to the lab data which is shown here. This compressibility is calculated from focal point pressure to this pressure. So at this one, we need to calculate it by the second equation here. And for those ones that are far from focal point pressure, we calculate them by first equation shown here. Do you see that equation? Is it? Yeah. Now we will do the same what we have done in with relative volume. Just you say pressure
What did you mean by place from
this is if you want to look to this plot and the reference and which equation is correct for each one, we will write this. You don't need to go that, but if you are interested, you can go. You can go there. I mean. Yeah. So. We say that you always have two pressure points. Oh. So it's So here we enter the lab data and we need to calculate the compressibility for our equation state, and we will compare the error percent. So here is like so now we have to take the relative volume at this pressure at 500 and then at 400, and we have to put them here and so on. And when we can find that, we can find that in equation of state values here. Relative volume from equation of state. So we need this value here, 5,000, 4,000, 3,000, and this, which is 1. And now we will apply the equations to calculate the compressibility. So here we are above bubble point. I will show that. We will use this equation, this one, for the first two compressibilities. And for the third one, we will use this one. So minus 1
To this point, what you got to
Yeah, this one we use the second one, only this one. Yeah, because we are calculating, we say here at pressure equal or near to the bubble point. So we use this equation as I already said. Near, you need 2 pointers to calculate the compressibility. From pressure, let's say the second value will be saturation pressure. So you will need to take another pressure which should be not far away as this range here. When you start having this curve, so you will need to, you can draw that data and say, okay, from this point I should apply this equation. And from here where I have straight line, and here you will define which pressure I should use this equation. Is that clear? If you draw that, and you will see your waveform looks like this, and then you. Actually, I don't have the book with me now, but maybe next time I will show you this plot. Yeah, I'm not sure if here we have. I think here relative volume. I have to review this to see this again to make sure. Which here we have taken the relative volume from equation of state, which we took from the software, because now we will compare from our equation of state and the lab data, measures data.
This one is just for if the lab already knows this. So for this first two, this one, we use this. We use the plus this whole. So for this one, we use
And this is the interface that you have in your compressibility.
so
It looks high, yeah. It's usually like this. But
11%.
if you match we don't care so much about this. We just indicate that we have error like this. But what we do in software, we try to make this match it with the lowest relative volume, not relative volume, match it as we can. And for this one, we usually can do anything. It's just we take indicator, and this one for compressibility, it's not like the relative volume. 10% it's okay for compressibility. It's not. It should not. I mean here because at each test you have values. For example, in CCE you should not have. I mean it's better to have below 1%. For DLE, you will see that it's better to have below 5%, but you will never be always below 1%. Also here for this one compressibility, it's okay to be 10%, 11%. You can use it. Yeah, that's it, I think, for today. And next time we will start working with DLE.
Thank you.